I'd like to invite Yossi from Tel Aviv University, who will be giving the last talk of the day on fast approximation algorithms for submodular optimization problems. Joint work with Yiftach Gamzu and Anrot.
And Ranroth.
Ranroth.
So I'm going to talk about fast algorithms. We're switching back to algorithms and not complexity. About submodular optimization. Assume that some of you are familiar with submodular, but I'll define it. And it's a joint work with Yiftach Gamzu and Ranroth, or two of my students. So let me first define what is a submodularity. Submodular functions are defined on subsets. So you have a set of elements, and you define on every subset of that you have a value. So it has 2 to the n possible values. And you define the marginal value. Given that you have a set, you want to compute what's the marginal value if you add one element to the set. So it's a value with the element minus the value before you add the element. So that's the marginal value. And a function is called submodular if you have a smaller set, then the marginal value is larger. Let me give you an example. So assume that you think about your dinner. So if you have already chicken, fries, and a muffin, and you're thinking about eating a cake, so the marginal value is smaller compared to the case that you have only chicken and fries. And yeah, and then unless you don't like fast food. But anyway, so that's the meaning of a submodular function. And we are also will be interested in what's called monotone functions. What does it mean, monotone function? If you have more, the value is larger. So that's a monotone. And also non-negative. So I'm thinking only about positive functions. And as I said, submodular it was defined before. The marginal value is larger if you have a smaller set. And sometimes you can also it's also defined formally by the last line there, that the function of A plus B is larger than function of the union plus the function of the intersection, but this is equivalent and this is much less intuitive in some sense, but it's equivalent definition, so we'll use the marginal value definition, which makes more sense. I mean, it's equivalent and easy as a better intuition. Okay, so let me give you an example of submodular functions. So for example, the coverage function. So here, again, the submodular function is on sets, on elements. So the elements are the sets here, and the value is the number of elements which are covered by the set. So for example, if the element is A, so that's confusing because the sets are elements. So if you want to see what's the value of a function of a set of a set A, so it's a number of elements in that set. If you want to see what's the value on A1 and A2, so it's the union of the two. So this is a submodular function because if you have more sets, then the value of additional set is smaller because it covers less extra elements. Let me just say that there are also natural examples where the function is not monotone. For example, a cut in a graph is a function of a submodular function which is not monotone. If you look at the set, the cut consists of S and T. If you look at the cut of a set S, at the beginning is smaller, then it might become larger, and then the set becomes eventually the whole graph, then the cut becomes 0. So it's a non-monotone function. But we are interested only, in this talk, we will be interested only on monotone functions. So you can forget about this example and think about sets and things like that. Okay, so now the problem with submodularity is that actually we have 2 to the n possible values. And the question is how we represent it. And in general, we need all the 2 to the n possible inputs. So in order to, what we will be interested in fast algorithms, not even polynomial, but usually linear or quadratic. So the standard way is just to use oracles. So what is an oracle? You give it a set, a value oracle, you give it a set of elements, and you just get a value. So this is how we will use how we define the function. Okay, so I'm going to talk about 3 separate problems. I'm not sure I have time to all of them. So if you sleep in one of these questions, you can wake up again in the next one, and just each one are defined from scratch. So that's so let's start with the first one, which is submodular ranking. So the definition at the beginning will sound not very natural, but then I'll give an example why it might be natural. So you have m items, and you have n monotone set functions. And what we are interested, so let me just remind you what is a monotone. If s is smaller than t, then the value of s is smaller than value on t. And the goal is to order the items. We have m items. We want to order them to minimize the average cover time of a function. So now I need to understand, to explain what does it mean by that, what this statement means. So I'll just explain each of this word. Let me explain what is an order. Order is a permutation. So I just need to decide which element I put first, second, and so forth until the nth one. I guess item, you know what it is, or let me continue. Cover time. Okay, I see that it's a bit, the box should be on cover time. What is a cover time? A cover time is the minimum index such that the function up to that index is larger than 1. So that's a cover time of a function. And the goal is to minimize the sum of the covers time. And when I see this slide, I don't understand anything. So let me just give you an example, because that's complicated, but that's a formal thing. And we'll see an example. It's very simple. Think about web search ranking. I'm not sure. There is some application now in the web which is called search. I'm not sure how many of you are aware of this. And this is one of your favorite search engine. This is a political way to say whatever. Don't want to choose a specific search engine. Politically correct way to say it. So let's say that we are looking for, say, Galaxy. So Galaxy might have various meanings. I'm not sure. I mean, it's good they cannot see what is there, but it can do a radio station. It's the galaxy in the astronomical a term, and there is also the LA Galaxy, which is a football team. So you have various. You're looking for a certain name, you are searching for some item, and you get possible pages. Let's say 1, 2, 3, and 4, so forth. And in addition, you have different users. So not all users are looking for the same thing. So here I'm thinking about 3 types of users. F1, F2, and F3, and each one is interested in different page. And let's say that each page has a different value for each user. For example, if I look at A32, this matrix actually tell me how much information I have for page 2 for user 3. So this is the amount of information that is relevant for that user. And that could be an arbitrary matrix for the users, because some users are looking for different things, and various pages have partial information for each one of them. So the goal, each user is actually scanning, once he performs the search, he's scanning the pages from top down, say, and once he collects enough relevant information, it stops the search. He stops looking because he got enough information and is not interested anymore. And what we are trying to do is actually to minimize the average expected time until the user finds enough information. So you're looking for a critical information, and once he finished, he stopped, and now we have different types of users. Each one may be weighted by the population, the proportion in the population, and we want to minimize the average cover time. So now you might understand what was the formal definition. So again, the formal definition is that I want to order the pages, the elements, and I have different types of users, F1, F2, and F3, for example. And once I put the pages and I look at the function, and once I look at a prefix, one of the value of prefix is above some threshold, let's say 1, then I'm happy, the user is happy, and therefore is not looking anymore, and this is its cover time. And what I'm trying to minimize is actually the average cover time over all types of users. So this is the motivation of the formal problem that I described before. And one thing to understand is that these pages do not necessarily have disjoint information. For example, if you're looking for galaxy, then I'm sure that you cannot see the two possible pages, 1 and 2, but one is actually the Wikipedia page, which has some information, and number 2 is the NASA page. So as you can notice, Wikipedia is more informative than the NASA page. They have more, they know more about the galaxy. So they appear before. And actually, but if you read both of them, let's say that in page 1 you have 0.9 information, and in page 2 you have 0.7. If you look in both of them, you don't necessarily have 1.6. You might have 1.2, 1.3, 0.94, and so forth. Certainly you have more than 0.9, 0.7, but there might be overlap, because therefore there is an overlap. So the way to describe it is actually the overlap can be captured by submodularity. So if you have more pages, then the extra value of additional page is not as large as if you would have less pages. So this is why it is captured by submodularity. So now let me just describe what function we are interested in. So we will consider two functions. One is that the function of the pages is actually additive. Then I assume that there is no overlap. So if I see each page as a value for each user, and once a user sees several pages, the value is just the sum of the values of the pages for that user. So again, pages for different users have different values. And the general case where we are looking at the submodular setting, which means that, again, every subset of pages for a user has a different value, which is a submodular function, and not necessarily the sum over the value of the pages. And of course, we need to use, as I said, in that case, we need to use a value oracle, because we cannot represent the function in a compact way. Specifically for the additive setting, of course, we can present it, because every page, we can represent it as a matrix. Okay, so let me, again, I mean, instead of this, since it's algorithmic things, and that's supposed to be real, because the problem was, we got the problem for real people, not from theoreticians. So let me give you an example. So let's say that you have here 4 user types and 4 pages. And you want to minimize, again, the order of the cover time of the function. So again, if you look at the function of a user type 2, and this is the value of the page 4, so I'm repeating the same thing like 75 times just to be sure that you understand the problem. And let's say that we choose the order 1, 2, 3, and 4, which is just a simple order. So now if you look, for example, for user 1, then is happy once, so at the beginning it gets information 0.2, then additional 0.7, so eventually you get 0.9, and then once you get 0.1, I'm just reading the first row, then he gets 1, and this is why he is happy. So the first user is happy after 3 pages. On the other end, the second user is happy after 2 pages, because he gets a 0.5, 0.6. Now he's above 0.1, because this is linear, there's no overlap. Therefore, is happy after 2 pages, and so forth. The third user is, again, after 2 pages, and the fourth user after 4 pages. So the cover time is actually 10, assuming all of them are weighted equally. However, if we look at the order 4, 2, 1, and 3, and this is how the matrix was permuted according to these columns, the columns has been changed. So if you can see easily that now the cost is decreasing, the first user is happy already after 2 pages because 0.6 plus 0.7 is already above 1, and so forth. For just reading the rows one after the other and computing how many steps I need to go until I'm over 1. Okay, so let me tell you what's known about this problem. So previously, the problem was considered only for the additive setting, and we were more concentrated on the submodular setting. So let's say that the function is only, let's say that the matrix is only 0, 1. This is actually correspond to the problem which is called mean-sum set cover. What does it mean, mean-sum set cover? It means that you have sets and you need to order them. And now, instead of usual set cover problem that you have sets and elements and you want to find minimum number of sets which covers all the elements. However, in the mean-sum set cover, you don't care about covering all the elements. You care about how fast you cover the elements. So you order the sets and you look at each specific element and you consider what's the cover time for it. How many sets, you look at the order, at what time it was covered, and now you average it over all elements. So this is the mean-sum set cover. So this is actually a special case of our problem where we are looking at the linear, the additive case, and all the matrix is 0 and 1. And actually, Uri Feig, Lazilovich, and Prasad et al., they showed that this problem has 4 approximation. Actually, the greedy algorithm is for approximation, and that's the best that you can hope for. So this is for this special case. Another special case is that the sum of the entries in each row is actually exactly 1. That means that you have items, you have elements in the matrix which are positive and elements which are 0. And since the sum in each row is exactly precisely 1, you actually don't care what are the exact values. You just care if it's positive or 0. Because now, if you order the elements, ordering the elements is actually permuting the columns of the matrix. For each user, the cover time for each user for each row, this is the user, is actually depending it's a minimum time when you cover all the stars. You don't care about the zeros, but you really don't care what is written in the stars because the sum of the stars is precisely 1, so you will be done only when you cover all the stars. Of course, you don't need to cover the zeros for the users. So this is a special case, and again, this has a 2 approximation, and this is by a reduction to some scheduling problem. And actually, 2 years ago, it was shown by the unique game conjecture that this is actually tight. Also, you get also 2. So then there are more problems now, not only about 0, 1 matrices, but again, only for the additive case. But each row can have only 1 type of value, either 0 or 1 value. Let's say 0.3, 0.3, 0.5, 0.5. And then, what does it mean? It means that you are looking, so in the search problem, what does it mean? That you are looking for certain number of pages, but you don't care which, as long as they are relevant. So there are relevant pages and non-relevant pages, and you are just looking for some relevant pages. And here, so this is again a special case, and here there was a sequence of papers that started with logarithmic approximation, but eventually it got to a constant approximation. Okay, so eventually we get to our result. What we show is that the additive setting, and again, additive setting, it means that you have a matrix and you just want to permute the matrix in such a way that the rows, each row will be covered as fast as possible. Then you can get actually a constant approximation. And I'm not going to talk about it. I'm actually going to talk about the submodular setting. And actually, I'm not going to talk in either one of them, but anyway, the submodular setting is what we show is a logarithmic approximation. And I'll just describe the adaptive residual update scheme, which we are using. And this is actually based unless P is equivalent to MP. The nice thing about this problem is it actually covers both set cover and min sum set cover. And since it's generalized set cover has a log n approximation, actually log n hardness, I mean. I think one of the proof it is in the audience here, in the second row. And so actually you cannot get better than a log n approximation. Okay, so now I'm going to describe the algorithm. If you forgot the problem, I'll remind you in a minute. So one obvious algorithm is that you want at each time to choose an element, to choose a column such that it will maximize your contribution to the problem. What does it mean? Suppose that you already decides on the first S pages in the search. You already selected certain number of pages, certain number of elements. Now you want to evaluate what's the contribution of additional element. What does it mean? You look at every additional element and you compute the function with the element, given the set that you already selected, minus the function with the element, which is the marginal value actually. But you cut it by 1 minus fi of s, because we are only interested to get information up to 1. User is happy once he gets information of 1. He doesn't want to get more, doesn't need to get more. So this is your contribution to a function, to a certain function. This is the contribution of element j to a function I, and now you just sum it up over all the function. So this is the last statement in the box. And you choose the element which has the maximum contribution. Again, it's hard, maybe it's hard, I mean, it's simple, but it's maybe hard to see from the slide. So examples are always better. Again, the users are the rows, F1 up to Fn, and the pages, the items are the columns, let's say 1 up to square root of n. Now, let's say that we want to order the column such that the cover time for the rows will be minimized. So let's say, of course, I mean, we'll start with the first column because it has a huge value for the users, actually much more than everyone else. It has something like n times n information, n times 1. Just a little bit information. Therefore, the first item, the first row will be chosen first. But now, if we look at the second row, sorry, the second column, the first column will be chosen first. And if we look at the second column, then the contribution is not so large. There are approximately n functions, and the contribution is 1 over n. So this is why the contribution of the second column is at most 1. So the greedy order will be, first of all, choose the first column. And then, since the second column has information which is less than 1, but the third column, from the third to the square root of n columns, it has large contribution. Okay, see that there are various interesting boxes here. So because let's say that the item number 3 is information 1 for the user here down there. So 3 rows from the bottom, or let's say the last item has huge information for the last user, and therefore I'll prefer to choose elements 3, 4, 5, 6 out to square root of n before I bother to put the second column. And this is easy to compute that the order will actually, the cover time for the users will be n to the 3/2, because most of the users, the first n users, will have to wait until the end until they'll be happy. And it will take them like a long time, square root of n times. Almost n users will have to wait square root of n times. Therefore, it will take n to the 3/2, while the optimum order is, of course, to use 1 and 2, and then many users are happy after 2 steps. And all the other users are happy later, and that will give you n times. Therefore, greedy is bad, which we heard several times today. greedy is bad, so we need to do something else. So the adaptive scheme is, so this is how we define the adaptive scheme, because the problem with the previous, let me see if, yeah, the problem with this thing, with this algorithm, the greedy, is that almost all users were almost happy. We just need a little bit of information, but we didn't take this into account, that they are almost happy. So now we want to take it into account. What does it mean? We do the same thing, assuming that you already have some pages that you picked in the order. Now we want to pick the next element. So we again compute the marginal value for each element, for each user. We kept it by 1 because we don't need more than 1. But now we weighted this a value by how close the user to be happy. If he's very close to be happy, then we give it more weight, because then we are actually going to make him happy soon. And making people happy is good. So, so this is why we have this weight. The weight is actually 1 over the remaining to 1. I mean, the value of the function, which is, the difference between 1 and that value. So items which are rows which are almost happy will give higher weights, and this will be finished faster. And this is the algorithm. Actually, again, let's take an example, because always example explains better than words. So let's take exactly the same example as before. We have these rows, and we want to order the columns, the items. So again, we start with 1 because the first column has the maximum information. It has huge amount of information, almost n. So we put it first. And now, at the beginning, all the users are equally happy. And now, we notice that actually almost all the first n minus square root of n users are actually very happy. They're almost happy, therefore they have very high weight. Since they're only missing 1 over n, they have huge weight, which is about n. And now, okay, so instead of weight 1, now they have weight n, all the first n minus square root of n users, and therefore we actually will choose 2, because the contribution of 2 is smaller for each user, but since the weight is so large, then overall the contribution of the second column is very nice, and therefore is chosen second, and so forth. And this algorithm, actually, what we prove is that this scheme is a log of 1 over epsilon approximation, where epsilon is smallest non-zero value, marginal value in the system, in the matrix, in the submodular function. And this is also optimal. There is a omega of log n hardness. So just to complete the story, since we got this problem for practitioners, and what's nice about algorithms is that actually you can explain the algorithm without explaining the proof. The proof is a bit involved. Actually, we found out that our algorithm gets a constant which is 4 times log 1 over epsilon. And recently, there is a paper which simplified the proof a bit, but gets a constant 80. So if you're ready to sacrifice the constant to 80 instead of 4, then actually you can get a much simpler proof. But anyway, when we came back to the practitioners and tell them about the algorithm, it took us like 2 years. They told us. They didn't say it in this way, but they say, thank you, but we're not interested anymore. It's too late. And, okay, so it stayed as a theoretical paper. Okay, so this is the first paper, first result. Now, just let me summarize. Fast deterministic, and actually the algorithm is really fast, because it's quadratic, and it's very, very simple, and it's very straightforward, easy to implement. There is a small issue here how to get this submodular function, which is not an easy problem, but given that, it's simple. Okay, and let me go directly to the second problem. So again, if you, you can wake up or go to sleep, again, whatever you want. Now it's we are starting from scratch. Submodular packing. Let's see. So here again, you have n items, but now you have m constraints. So this is like the classical linear programming thing. You have m constraints, ax smaller than b. You have n items, and we notice, I think I missed it here, the function a should be a positive. Oh no, it's written. A is only, it's positive matrix, which contains only values, positive values, and we normalize it like it's between 0 and 1. And now, let's assume, we can assume without a loss of generality in some sense that the b, the 3, we want to solve a x smaller than b, so the b's are only number which are larger than 1, because if they are smaller than 1, then actually we can omit an element, but it's simpler to see that we can only, we can reduce it easily to this case. And now we have a submodular functions. Yeah, I'm not sure why there are all these boxes here. I'm not sure that you see them, but you have here a matrix, and now you want to choose subset of this element, so that you have variables. It's a matrix. Yeah, you have variables. And you want to choose subset of them and make them 1, and all the rest are 0, such that it will satisfy all packing constraints. Why it's a packing constraint? Because it's smaller or equal to, and all values are positive. So it's a packing constraint. Each constraint, we have here m constraints. Each one of them is a packing constraint overall. It's a packing constraint. So we want to find subset of the elements, make them 1, all the rest are 0, such that all constraints will be satisfied. Of course, for that case, you can choose everything 0. That's fine, but you want to maximize some submodular functions on these variables. So let me just to explain it, let me think about the linear case. So the linear case is well known. Actually, you have n items, you have m constraints, you have a linear function. This is just integer packing linear programming. This is a standard classical problem of ax smaller than b. All values should be 0 and 1. I mean, it's not the most generality, because we assume that matrix is non-negative, and we want to minimize a linear function. Now we want, instead of linear function, we want to extend it to a submodular function. The submodular goal function instead of submodular linear function. Instead of linear function, we want to replace the goal function. So let me tell you what is known about linear function. Linear function is one of the most well-studied problems. We want to solve linear function, integer linear programming with a linear goal function. So this is a very hard problem in general, and there are like 3 types of algorithms to try to attack this problem. First of all, solve the LP fractional problem, fractional relaxation. Assume that variables instead of 0 and 1 will be between 0 and 1. X, instead of being either 0 or 1, it's between 0 and 1. And then use the classical method of randomized rounding. This is the LP approach. There is a hybrid approach which instead of solving the linear programming using the ellipsoid algorithm, which is polynomial time of the interior point, you solve it combinatorially, and you can do it in some way a little bit faster. And then you apply randomized rounding again. And the third approach is actually solve it using primal dual algorithms combinatorically all the way. So this is for linear function. What is the best? So again, I mean, the problem is so general that actually it contains almost, not all, but many, many problems. The list is so long that I didn't want to, click, independent set, routing, whatever you want. And this is why it's so general that it's very hard to solve it. This is why it doesn't give you so much. But if you want to solve the general problem, the way to characterize the solution is according to the width of the linear program. What is the width of the linear programming? Is actually since the matrix contains only value between 0 and 1, so you look at the B column, the 3 column, the column with the I mean, AX is smaller than B, you look at the B column, and if the minimum value in that column is actually the width. If the minimum value is large, it means that it's easy to satisfy this matrix because you can put more elements which are 1. Because you choose many you have many variables which are 1, you don't contradict the constraint. If B is small, it's much harder. So this intuition actually is what's happened really in reality. I mean, if you call it reality. What's known about the linear case is that if the width is W, then the approximation is M to the 1 over W. Specifically, what's become very nice, if the width is log M over epsilon squared, let me just remind you, M is the number of constraints, then you actually get 1 plus epsilon approximation, which is very nice. This is certainly great. So if all the matrix consists of elements which are between 0 and 1, and the 3 column is actually at least log M, which is not so large, log M over epsilon squared, and you actually get 1 plus epsilon. So this is the linear case. We want to go to the sublinear case, to submodular case, okay? Actually, this has been solved and, by Kaniskeo, Chekuri, Pale von Drack in a couple of years ago, and actually they achieved the same approximation. And when the width is large, log n divided by epsilon squared, actually they get E over E minus 1 and not 1 plus epsilon, but this is actually the best possible. However, their algorithm is actually some type of interior point. It's a continuous greedy approach, and this approach is not very practical. What does it mean? It's complicated. It's not fast. So it's something like n to the 6. So if n is not too large, today in today n, like a million is very small n. So 2 to the 20 to the power of 6 is 2 to the 120. It's not feasible. I mean, yeah, it's not. It's really, I mean, it's efficient in theory, but not in practice. So we want to find an algorithm which is also will be supposedly efficient in practice, not necessarily, but supposedly. And also this algorithm is randomized, and we are looking for fast deterministic combinatorial algorithm. So, okay, so let me again tell you what's the problem. The problem is that it's the most simplest problem. I never saw a simpler problem. You have a matrix A times X smaller than B, just a linear program, an integer linear programming, but instead of maximizing linear function, you want to maximize submodular function. Okay, so we actually get the same results, which is fast combinatorial algorithm, which is it's about n squared, so it's really much faster. So if n is even 2 to the 30, to the 25, it can be implemented. And it gets the same approximation, m to the 1 over w. Again, w is the width of the linear programming, which means that it's the minimum value in the column, in the B column, assuming all values are between 0 and 1. And again, the limit when w is large enough, which means log m over epsilon squared, it's getting approximately E over E minus 1, because you cannot get better than that. And the algorithm is based on multiplicative Aptitz method, and I'll just give you the algorithm here. That's the whole algorithm. And let me try to explain it. I mean, it looks, that's a full complete description, so I'll try to explain it. Actually, yeah, I explain it by the example on the right. So we have here constraints and we have variables. The algorithm, we just choose element one by one. We just select one element, we make it 1. Select another element, make it 1, and so forth. It's a one time, you go one time over the elements. I mean, you choose it in certain order, but you choose an element to be 1, and then an element to be 1, and then an element to be 1. Like this. It's a very simple algorithm. And the question is, which element once I chose several elements to be 1, what's the next element to be 1? So actually, so I'm computing, first of all, I'm computing for each constraint how sensitive is this constraint? I mean, how bad is this constraint? So AX times S is actually the, I already choose here 1 and 1, so it's 0.8 times 1 plus 0 times 1, so it's 0.8, so it's not very tight. The constraint is not very tight. So I'll take some lambda and take it to the exponent of 0.8 divided by 3. So this value tells you how much tight the constraint is, each constraint is. Which means I already choose some elements, I compute the value of that constraint, and I just want to see how tight is it compared to the BIs. And now I just normalize it with 1 over BI, this thing, and this is how dangerous is each such constraint. So I'm just getting a value for each constraint, which means how dangerous it is. And now I'm just looking at each possible variable. I already choose x1 and x4, and now I'm debating between x2 and x3. Of course, there could be many more elements, but let's say that I'm debating between the two. So I'm just looking at let's say at the x2, I'm multiplying 1 by the value of this constraint, plus 1 by the value of this constraint, by 0.3 by the value of this constraint, by 0 the value of this constraint, and I'm getting a value here. And I'm doing the same thing for x3. I mean, here it's 0 and 0, 0.5 times the value of this constraint plus 1 times the value of this constraint. So I have here two elements. For each one, I'm computing how costly it is. This is the CI. And now, so this is, if the cost is large, so it's going to be bad because the constraints are going to be close to their limit. So now I'm actually choosing the element but now we need to take into account that the contribution of each element is different. So given that you already chosen one here, x1 and x4, I'm looking at the goal function and computing what's the marginal contribution of x2 and x3. And if the marginal contribution is large, I might want to have it there. So what I'm just doing here, so here you see the f of s is the marginal contribution. So I'm looking at the value such that the cost divided by its benefit is minimized. So that would be a good element. Because if the cost is small, it's not going to, the constraints are not going to be problematic, but and if a value is large, then it's great. Okay, I think that, and actually this is the whole algorithm. That's it. I didn't hide anything, I just hide the proof, but that's a minor issue. And we get the same approximation. And the third thing, I don't think I have time, is just about submodular, so maxat, but okay, but I mean, it's better. Up to 8 I have, so I have 2 hours, two more hours, no? Okay. So, okay, I think I'll just skip it and go to the, yeah. So what I wanted to tell you about is a fast combinatorial algorithms for ranking, for packing, and for maxat, which I didn't have time to. And actually, it's fascinating because all the problems that you are aware of, all the problems that we know of are usually linear. And now every problem that you know, you can actually think about the submodular version. Because we always, in most of the problems that we think of, we always think about the linear version. Assume that the goal function is linear in some sense. And now we have a huge number of problems now where the value is submodular instead of linear, and that makes sense actually both in reality and in theory, which are in both far away from each other. And that's it.